By the close of the 17th century, it had been believed, with a confidence rarely equaled in the long record of human thought, that the motions of falling bodies, the swing of pendulums, and the wheeling of the planets had at last been reduced to a single mathematical order that would stand for as long as the heavens themselves. That confidence did not arrive suddenly, and it did not stand alone. It was only the most recent chapter in a much older habit of the human mind, the habit of composing a rulebook for the world and, upon completing it, declaring the composition finished. The earliest of those rulebooks had been written without instruments, without laboratories, and without the mathematics that later generations would come to regard as inseparable from natural knowledge. It had been written by observers who possessed only their eyes, their patience, and the long inheritance of what earlier observers had already claimed. Aristotle, in the middle of the 4th century BC, set down in his Physics and in the treatises that followed a cosmos that his students and their students would carry, in various forms, for nearly 2,000 years. In that cosmos, every substance possessed a natural place toward which it moved when nothing hindered it, so that stones fell because earth belonged below, and flames rose because fire belonged above. The world beneath the moon was made of 4 elements in restless combination, while the world above the moon was made of a 5th substance that neither aged nor decayed, turning in perfect circles because circular motion alone befitted the incorruptible. Nearly 5 centuries later, in the 2nd century of the Common Era, Claudius Ptolemy, working in Alexandria, gave that cosmos its most durable mathematical dress in the treatise later known as the Almagest, laying out a geometry of nested spheres, deferents, and epicycles capable of predicting the positions of the wandering stars with a precision sufficient for astrologers, calendar makers, and navigators alike. In the middle of the 14th century, Nicole Oresme, writing at the University of Paris, offered commentaries on Aristotle that quietly entertained the possibility of a turning Earth, yet even he did not step outside the framework so much as press gently at its edges. The Aristotelian rulebook was not, in its own time, a foolish rulebook. It accounted for what could be seen, it agreed with the ordinary experience of weight and rest, and it possessed the dignity of a system in which physics, cosmology, and metaphysics spoke together in one voice. Beneath its surface, that first rulebook already carried something that would outlast it. It insisted that quantities in the world were not created and not destroyed without cause, that substance persisted through change, and that the celestial order was fixed in its arrangement even as it turned. The instinct toward conservation, toward the recognition that something in nature is preserved when appearances shift, was present at the beginning, though it wore the language of substance and place rather than the language of measured quantity. That instinct would prove more durable than any of the doctrines that first expressed it. The dismantling of the Aristotelian world did not begin with a single stroke. It began, rather, with the patient work of observers who insisted on measuring what earlier generations had been content to describe. Galileo Galilei, rolling bronze balls down inclined planes at Padua between 1604 and 1638, discovered that the distance a body falls grows as the square of the time, a regularity that no doctrine of natural place could produce and no appeal to the elements could explain. Johannes Kepler, sifting through the observations that Tycho Brahe had bequeathed to him, published in 1609 the first 2 of the laws that would bear his name, showing that the planets moved not in circles but in ellipses, and in 1619 he added the 3rd law, binding the period of each planet to the size of its orbit through a proportion that no epicycle could mimic. The heavens, it turned out, were geometrical in a way that the ancient astronomers had not suspected, and the geometry was not the geometry of perfection, but the geometry of measured motion. It fell to Isaac Newton, in the Philosophiae Naturalis Principia Mathematica of 1687, to gather these discoveries and to bind them, together with his own laws of motion and his law of universal gravitation, into a single mathematical structure that could account, in one breath, for the fall of an apple and for the orbit of the moon. Almost at the same time, Gottfried Wilhelm Leibniz, working along a parallel line in Germany, developed in 1686 the concept of vis viva, the living force. which he argued was preserved in the collisions and motions of bodies. The two men differed sharply over priority, over metaphysics, and over the meaning of the calculus that each had, in his own way, invented, yet between them they set down the terms in which the next paradigm would speak. That paradigm carried much from the world it had unseated, though it did so quietly. It kept the conviction that the cosmos was a fixed order obedient to law, and it kept the older instinct that something in nature was preserved through every change, though it now gave that instinct precise mathematical expression. Where Aristotle had spoken of substance persisting, Newton and his successors spoke of momentum, the product of mass and velocity, which was preserved in the collisions of bodies, whatever the details of the collision might be. Where the medieval commentators had spoken of the fixity of the spheres, the 18th century learned to speak of angular momentum, preserved in the turning of every isolated system, whether a spinning top on a table or a planet in its orbit. What was discarded was the doctrine of natural place, the division of the cosmos into two realms of unlike substance, and the notion that motion required a purpose to explain it. What remained was the deeper conviction that beneath the changing face of the world, there were quantities that did not change, and that these quantities could be counted, measured, and predicted. The confidence that Laplace expressed in the opening years of the 19th century rested on a picture in which the world was a vast assembly of particles pulling and pushing one another across empty distance, and that picture began to strain almost as soon as it had been drawn. The strain did not come from philosophers questioning the foundations. It came from workshops, from laboratories fitted with coils of wire and jars of chemical solution, and from the patient hands of experimenters who found, again and again, that the world contained influences which no arrangement of particles and forces at a distance could readily explain. Michael Faraday, working at the Royal Institution in London through the 1830s and beyond, was the figure in whom that strain first became a new way of seeing. Trained as a bookbinder rather than as a mathematician, he approached electricity and magnetism through the sensitivity of his fingers and the discipline of his notebooks, and beginning in 1831, he demonstrated that a changing magnetic influence in one coil of wire produced a current in another coil that touched it nowhere. The influence, whatever it was, crossed the space between them. Faraday came to speak of lines of force filling that space, curving from magnet to magnet and from charge to charge, and though his colleagues at first regarded the language as a picturesque aid to intuition, he insisted that the lines were the reality, and the bodies at their ends were merely the places where the lines terminated. The rulebook of the previous century had described action at a distance as a bare mathematical fact. Faraday was proposing, without quite saying so, that the space between bodies was itself a stage on which physics happened. It was James Clerk Maxwell, working in Aberdeen and later in Cambridge, who translated that proposal into the language the rulebook would accept. In a series of papers culminating in the treatise of 1873, and most decisively in the equations he set down in 1865, Maxwell showed that Faraday's lines of force obeyed a compact set of relations that bound electricity and magnetism together as two aspects of one field, and that this field could support waves traveling through empty space at a speed which, when calculated from purely electrical and magnetic measurements, matched the measured speed of light to within the precision of the instruments then available. Light itself, it turned out, was the trembling of the field. The rulebook now contained a new kind of entity, the electromagnetic field, which was not a body and was not a force between bodies, but a continuous presence spread through space, carrying energy from one place to another at a definite speed. What had been preserved from the earlier paradigm was the conviction that quantities of energy could be counted through every transformation, and that conviction now extended into a realm the older mechanics had never entered. What was quietly discarded was the notion that the space between bodies was empty and inert, though the full consequences of that discarding would take another 2 generations to unfold. At the same time, along a line of inquiry that seemed at first entirely separate, another difficulty was reshaping the rulebook from a different direction. Steam engines had been running in the mills and mines of Europe for the better part of a century, and the men who studied them had begun to notice that heat, unlike the tidy quantities of mechanics, refused to move freely in both directions. Sadi Carnot, in his short treatise of 1824, had already shown that the efficiency of an engine was bounded by the difference between the temperatures at which it took in heat and released it, no matter how cleverly the engine was built. Rudolf Clausius, working in Berlin, took up that insight and in 1865 gave it a name that would enter the rulebook permanently, coining the word entropy for the quantity that measured, in his phrase, the transformation content of a body. Entropy was not preserved. It grew in every isolated system, and its growth marked the direction in which time itself seemed to run, from the hot toward the cold, from the ordered toward the mixed, from the possible toward the accomplished. The rulebook now held, side by side, a quantity that was conserved and a quantity that was not, and the two together described the world more completely than either could alone. The deeper meaning of entropy was drawn out by Ludwig Boltzmann, working in Vienna through the 1870s. In a paper of 1877, he proposed that the entropy of a gas was, at bottom, a measure of the number of ways in which its unseen particles could be arranged while producing the same visible appearance. Heat, temperature, pressure, these were not fundamental properties of matter, but statistical properties of enormous collections of particles too small and too numerous to track individually. The rulebook, which had been written in the language of exact trajectories, was learning to speak in the language of probabilities, and it was learning that the arrow of time, which mechanics alone could not explain, arose from the overwhelming likelihood that disordered arrangements outnumbered ordered ones. Josiah Willard Gibbs, working in almost complete isolation at Yale through the 1870s and 1880s and publishing his mature treatment in 1902, gave that statistical vision its most general form, introducing the ensemble as a mathematical device for reasoning about the possible states of a system without pretending to know which one it actually occupied. The rulebook had acquired, for the first time, a formal way of admitting that its own knowledge of the world was incomplete, and of turning that incompleteness into predictions of remarkable accuracy. Through these decades, the conservation instinct that had been present since the earliest paradigms held firm and, indeed, grew stronger. Energy, which Helmholtz had gathered into a single principle at the middle of the century, was now shown to move through the electromagnetic field as freely as through the collisions of billiard balls, and to change its form from mechanical to thermal to radiant without ever changing its total. James Prescott Joule, in the 1840s, had established through painstaking experiments in a Manchester brewery that a definite quantity of mechanical work always produced a definite quantity of heat, and the unit that would later bear his name would attach that equivalence to every calculation in the physics that followed. Momentum and angular momentum, inherited without modification from the Newtonian era, continued to be preserved in every experiment that could be devised to test them. The rulebook was being rewritten around these quantities rather than in spite of them. The next decimal place, as it happened, was where the rulebook broke. Max Planck, addressing the German Physical Society in December of 1900, proposed as a mathematical device that the energy exchanged between hot matter and the radiation it emitted came in indivisible portions proportional to the frequency of that radiation, and he introduced a small constant, which he denoted with the letter h, to fix the size of those portions. He regarded the proposal, at the time, as a piece of formal bookkeeping that saved the observed distribution of colors emitted by a heated body without demanding any deep revision of the underlying physics. 5 years later, in the papers he sent from the patent office in Bern in the spring and summer of 1905, Albert Einstein took the proposal at its word and argued that light itself was composed of such indivisible portions, and in the same remarkable year, he set down the special theory of relativity, in which absolute space and absolute time, inherited without serious challenge from the earlier paradigm, were quietly withdrawn from the rulebook and replaced by a geometry in which the speed of light held the position that Newton had reserved for absolute rest. 10 years later, in November of 1915, Einstein completed the general theory of relativity, in which gravitation ceased to be a force acting between bodies and became instead the curvature of a four-dimensional geometry shaped by the mass and energy it contained. Arthur Eddington, sailing to the island of Principe to observe the total eclipse of May 1919, measured the deflection of starlight as it grazed the limb of the sun and reported a value consistent with the new theory rather than with the old, and the result, announced in London that November, made Einstein a figure known far beyond the community of physicists. The rulebook had accepted its first genuinely non-Newtonian chapter, and it had done so without surrendering the conservation instinct that had guided it from the beginning. Energy and momentum were still preserved, though they were now inseparable components of a single four-dimensional quantity, and mass itself was revealed as a form of energy through the equivalence that Einstein had written down in 1905. While relativity was being drawn out to its full extent, a separate and stranger revision was gathering in the study of the atom. Niels Bohr, working in Copenhagen in 1913, proposed that the electrons, circling the nucleus of an atom, occupied only certain permitted orbits, and that they emitted or absorbed light only when they leapt between them. Werner Heisenberg, in a paper of 1925, composed on the island of Heligoland where he had gone to recover from hay fever, replaced the orbits themselves with tables of numbers describing the possible transitions. And Erwin Schrödinger, working in Zurich in the early months of 1926, produced the wave equation that would carry his name and that offered a second, superficially different mathematical language for the same underlying physics. Paul Dirac, at Cambridge in 1928, wrote down an equation that combined the requirements of quantum mechanics with those of special relativity and found, to his own surprise, that it predicted the existence of a particle with the mass of the electron but the opposite charge. Carl Anderson, examining cloud chamber photographs at the California Institute of Technology in 1932, identified precisely such a particle in the tracks left by cosmic rays and named it the positron. The rulebook had begun, for the first time, to anticipate the existence of matter that had never been observed and to be vindicated when that matter was later found. The deepest reformulation of the conservation instinct in this period came not from a physicist, but from a mathematician working at the University of Göttingen. Emmy Noether, in a theorem published in 1918 at the request of David Hilbert and Felix Klein, demonstrated that every continuous symmetry of the laws of physics corresponds to a conserved quantity, and that every conserved quantity is, in this precise sense, the shadow of a symmetry. Energy is conserved because the laws of physics do not change with the passage of time. Momentum is conserved because the laws of physics do not change from place to place. Angular momentum is conserved because the laws of physics do not change with the direction one faces. The instinct that Aristotle had expressed as the persistence of substance, that Newton and du Châtelet had expressed as the preservation of momentum and living force, that Helmholtz had expressed as the constancy of energy across every transformation, was at last shown to be no accident of experiment, but the necessary consequence of the world's indifference to when, where, and how it is observed. The conservation thread that had run through every earlier paradigm was, in 1918, given its final explanation, and every rulebook written thereafter would be written within the constraint that Noether had identified. From that constraint, the next paradigm was assembled, piece by piece, across the middle decades of the 20th century. Murray Gell-Mann, at the California Institute of Technology, and George Zweig, then a student at the same institution, proposed independently in 1964 that the proton, the neutron, and the growing menagerie of related particles produced in the new accelerators were themselves composed of smaller constituents, which Gell-Mann named quarks and which Zweig called aces. Peter Higgs at the University of Edinburgh, together with Robert Brout and François Englert at Brussels, and three other physicists working along similar lines, proposed in the same year a mechanism by which certain particles could acquire mass through their interaction with a field that filled all of space, breaking a symmetry that would otherwise have required them to be massless. Sheldon Glashow, Abdus Salam, and Steven Weinberg, working across a decade that culminated in the papers of 1967 and 1968, showed that electromagnetism and the weak interaction responsible for certain forms of radioactive decay were two aspects of a single electroweak force, unified at high energies and separated at low ones by the very mechanism that Higgs and his colleagues had proposed. The experimental confirmations arrived across the following decades with a regularity that recalled, though it did not equal, the confidence of the closing 19th century. Carlo Rubbia and his collaborators at the superproton synchrotron at CERN announced in January of 1983 the discovery of the W boson, and in June of the same year the discovery of the Z boson, both at masses that the electroweak theory had predicted. The top quark, the heaviest of the 6 that the theory required, was identified at the Tevatron Collider at Fermilab in 1995. And on the 4th of July, 2012, in an auditorium at CERN, filled with physicists who had waited most of their working lives for the announcement, Fabiola Gianotti, speaking for the Atlas collaboration, and Joe Incandela, speaking for the CMS collaboration, presented independent measurements of a new particle whose properties were consistent with the Higgs boson that had been proposed 48 years earlier. The rulebook that would come to be called the Standard Model was, at that moment, complete in the sense that every particle it required had been observed. It was not, however, complete in any deeper sense, and the physicists who had assembled it were the first to say so. It contained no description of gravitation, which remained the province of Einstein's geometry and refused to be reconciled with the quantum framework that governed everything else. It offered no account of the dark matter whose gravitational influence had been inferred from the work of Vera Rubin and Kent Ford at the Carnegie Institution in the 1970s to hold galaxies together against the pull of their own rotation. It could not explain why the universe contains matter at all, rather than the equal mixture of matter and antimatter that its own symmetries would seem to demand. And it depended on some 19 numerical parameters: the masses of the quarks and leptons, the strengths of the interactions, the details of the Higgs field, that the theory itself could not predict and that had to be measured and inserted by hand. It was in the search for the missing pages, rather than in any hope of overturning what had already been written, that the LHCb collaboration at CERN turned its attention to the rare decays of the B meson, the particle in which a beauty quark is bound to a lighter partner. Among those decays, one in particular offered the still pond conditions that the physicists of an earlier chapter would have recognized immediately: the transition in which a beauty quark converts into a strange quark with the emission of 2 muons, a process forbidden at the simplest level of the theory and permitted only through the loops of virtual particles that give the diagram its curious resemblance to a penguin. The rate of the decay was measured across the runs of 2011 through 2018 and again in the campaigns that followed, and the rate was consistent with what the Standard Model required. The angular distribution, however, the pattern of directions in which the muons flew away from the point of decay, encoded in a quantity that the theorists had constructed with great care and had named P5', was not. The discrepancy had first appeared in the analysis published in 2013, at a level of statistical significance that no one, at the time, was willing to treat as decisive. It had persisted through the analysis of 2016, at roughly the same size and in the same direction. And in December of 2025, when the LHCb collaboration presented the combined analysis drawing on the largest sample of B meson decays ever assembled, some 650 billion of them accumulated across the successive runs of the collider, the discrepancy had grown to approximately 4 standard deviations from the value the Standard Model predicted. The counts of the decays continued to respect every conservation law that Noether's theorem had established. The shape of the angular distribution, which is governed by the symmetries that generate those conservation laws, did not. The rulebook was not being violated at the level of what is preserved. It was drifting, quietly, at the level of the symmetries from which preservation itself descends. For those who have followed this long chronicle of how confident rulebooks have given way, one after another, to the rulebooks that succeeded them, this channel offers further studies of ideas across their paradigms, the long arcs of matter, of measurement, of the instruments through which the world has been examined, and a subscription is a quiet way to follow the next chapter as it is prepared. Each of the rulebooks that has passed through this account was true within its measurable reach, and no more. Aristotle's cosmos was true within the naked eye and the observations that eye could gather across a human lifetime. Newton's mechanics was true within the pendulum, the telescope, and the terrestrial laboratory in which forces could be applied and their effects timed. Maxwell's electrodynamics and Boltzmann's statistical mechanics were true within the galvanometer, the interferometer, and the vessels in which gases could be compressed and heated with precision. Einstein's geometry and the quantum framework of Bohr, Heisenberg, Schrödinger, and Dirac were true within the spectroscope, the cloud chamber, and the eclipse expedition that could measure a fraction of a second of arc against the disk of the sun. The Standard Model has been true within the collider and the vast detectors that surround its collision points, and it has been true to a precision that none of its predecessors could have imagined. The 4 sigma drift now appearing in the angular distribution of a decay that occurs roughly once in a million B mesons is not a failure of that truth. It is the familiar signal that measurement, having refined itself once again, has extended past the reach within which the current rulebook was written, and that somewhere in the pages still to be composed, the next paradigm is quietly waiting for the figures who will set it down.